Hi, this is Professor Fernandez. We are working on class notes B in lesson 19. Just like the previous class notes, previous example, we are once again going to draw the phase portrait near the equilibrium point 0, 0, the only equilibrium point of this system. And as I said earlier in that example, you could, based off of everything we've learned so far, have derived the eigenvalues and eigenvectors for this system. I've given them to you, however, because I want to really focus on the new skill in this lesson, which is sketching the phase portrait of these systems. So I'm going to follow a very similar analysis that I did in the previous video. So if you have some questions about why I'm doing what I'm doing, I'll refer you to that video. The first thing I'll do, as I did before, is sketch the basic parameters that we're going to use for the phase portrait. So first thing is I'm going to draw the eigenvector -1, 1, so -1, 1. And then again, I'm going to extend that to a line. We talked about why we did that in the previous video. And then I will draw the eigenvector, let's see, I'll put it in black, 2, 3. So 1, 2, 1, 2, 3. So there we go, that's that eigenvector. Great, and then what I'm going to do is analyze each part of this solution. So the general solution to this system, based off of everything we have learned in the class so far, is e to the lambda 1t times its eigenvector, plus e to the lambda 2t times its eigenvector. Okay. That's a C2 here to not confuse anyone. C2. Great, and I'll do the two-part analysis that I did before. As t goes to infinity, the solution x of t, unlike the previous example, does not go to 0, 0, because this part of the solution has a positive 4t. So depending on whether C2 is positive or negative, right, we might be approaching some version of infinity. So I'm going to say plus or minus infinity, infinity. Right, so that means that this system is unlike the previous one, where no matter where you started, you ended up at the origin. The orbits here are, no matter where you start, you're going to end up like way far away from the origin. We don't know in which direction. All right, so I can't really denote that or signal that in the phase portrait. But the second part of the analysis is going to involve, what about these two lines themselves, right? How do I get directions for those two lines? All right, so now that I know that not everything ends up in the origin, in the previous example I could have started there and that would have told me that the direction of the lines is just toward the origin. So I'm sort of speeding up the analysis in this video, knowing that you've watched the previous one. So I can't get any useful information from this, so I'm going to try something else. So I am now going to go to the individual eigenvectors and see what happens. So if I consider C2 to be 0, which again would happen for certain initial conditions, and I just look at this part of the solution, the limit as t goes to infinity of this part of the solution is 0, 0, because this is a decaying exponential. All right, so what does that tell me? That tells me that if I start on this part of the solution, which was -1, 1, it was this line. If I start on this line, then I end up at the origin. So what I'm going to do then is denote that on the phase portrait by these arrows going to the origin. Great. So that's good information. Let me go back and do the analysis for the other half of the solution. So suppose I choose an initial condition that makes C1 0. So I'm looking only at this part of the solution. What happens as t goes to infinity there? Well, that's what we just talked about a little bit earlier. E to the 4t goes to infinity, and it could be plus or minus depending on the value of C2. But the point is that I definitely don't go toward the origin. So I go away from the origin. So I'm going to go back to my phase portrait, and for this line, I'm going to now add direction that is away from the origin. Okay. So at this point in the analysis, we could continue doing what we did in the previous video, right? I have filled in the directions along the two lines that are created from the eigenvectors in the problem. And in the previous video, what I did was I considered these 4 regions and try to see what happened in those 4 regions to the system, what type of orbits it displayed. But in this example, I'm not going to do that because you can see, for example, let me pick on this region. You can see what's going to happen. If I choose a point here, well, that's kind of close to this portion of the face portrait. So it's going to come in to the origin. But eventually, if I get very, very close to this portion of the face portrait, this is going to push me away from the origin. So really the only way that this can happen is if this orbit kind of curves and connects and goes away from the origin. And that's kind of a clue as to what happens in every region of this face portrait. If I start over here, I'll see a similar phenomenon. I come into the origin, but then the black portion of the face portrait pushes me away from the origin. Same deal over here. I come into the origin, the black portion pushes me away from the origin. So it's a lot easier to draw the face portrait for this type of system. Again, we're going to give this a name in a minute, because what you get are all these hyperbolic orbits that are hyperbolas. All right, so in this case, in the video before, we call the equilibrium solution, 0, 0, to the system, a stable node. Everything just got sucked into the origin no matter where you started. In this system, that's not true. You do get sucked into the origin no matter where you start, but then when you get close enough, you get thrown away from the origin. So we call this equilibrium point a saddle. And again, later on in the lesson, we are going to relate these pictures to the eigenvalues of the system. And we're going to, I'll give you a handy little table that will show you all of the different names that we use for face portraits for linear systems. But the takeaway from this system is that, again, speeding up the analysis a little bit, the system does not suck you into the origin no matter where you start. It, in fact, does it for a little bit and then it throws you away. So this has qualitatively different behavior than the system in the first class notes. One of the reasons why we call this unit the qualitative theory of ODEs.